Okay, so we're going to be introducing the basic concepts in matrix structural analysis. But to do that, we really need to take a step backwards, and we need to take baby steps, right? We need to walk before we or crawl before we walk, so to speak. So to do that, most of you maybe not don't have a background in linear algebra, so I want to just start by kind of introducing some of the very basic matrix algebra notation, some of the definitions, some of the terminology. We're not going to focus a lot on the real matrix manipulation, so to speak, but we need to understand the basic matrix definitions and the basic matrix algebra and kind of just how matrices are set up and how they work. So we want to talk about that. We're going to introduce that in this video. We're also going to talk in this video a little bit about some of the basic definitions and concepts that we use in matrix structural analysis and the finite element method, things like degrees of freedom, the different coordinate systems, so that we can have a good understanding of that. So when we're using that terminology throughout the course and throughout your careers, when you hear that terminology, you understand what that means. So that's what we really want to address in this video here. So we want to start with some of the basic terminology in matrix algebra and matrix notation. So really, the first thing we talk about, what is a matrix? I've said matrix many times. We've been talking about matrices. I hope at least from the basic introduction that we've talked about, you at least have a general understanding. But by definition, what a matrix is, it's a rectangular array of quantities that are arranged in rows and columns. That's what it is by definition. We often use these as an aid in expressing and solving systems of expressions of algebraic equations. What we would generally say is uh, linear equations of solving linear equations. So linear systems of equations is the terminology that we would typically use. Now we say it's a rectangular array of quantities. Sometimes we can have a very special, I guess you could use, quote unquote, type of matrix, type of rectangle, and that would be a rectangle that has a one column. So if it has one column, we'd call that a column matrix. So if it has a single column, we'd call it just a column matrix, and it looks something like these. So in structural analysis or matrix structural analysis, we would say that the force matrix uh, or the force vector. So a column matrix is also known as a vector. So a vector quantity is a column matrix. So the force vector is a column matrix, or the displacement vector is also a column matrix. So it can have a unlimited number of rows, but has a single column. We could also talk about a square matrix. So a square matrix is something that has the same number of rows as it does columns, hence it's square. But a matrix doesn't have to be a column or a square, but in matrix structural analysis, we're often dealing with square or column matrices. So again, if it's a column matrix, we also typically call it a vector. You'll notice a couple of things here that I would like to point out to you. Um, if we use these kind of squiggly brackets about it, we're talking about a column matrix or a vector. If we use these square brackets, then it's just a rectangular matrix of any size. It could be a column matrix, or it could be a square matrix, or it could be anything. A couple of other things. I'm sneaking in some terminology for matrix structural analysis here too. If we use a lowercase k, that's what we're going to call our element stiffness matrix. We'll talk about that in later videos. If we use a capital K, that's our global stiffness matrix. One other thing to note here, we've got this notation within the matrix. So you see we've got the large letter, that would be whatever the number is in here, and then we've got this double notation. So like K11, K22, K12, K21. These are referred to as the coefficients. If you're in the stiffness matrix, they're referred to as the stiffness coefficients. Um, it's really important the order of these numbers. The first number represents the row that it's in. So if you notice along this top row, they're all K1 and then another number. In the second row, it's K2. In the bottom row, it's KN. And the second one is the column that it's in. So the first column are all K1. the second indice. The second indice in the second row is K2. If there's a third row, it would be K3. And the last row, the last indice in this example is using KN. So that notation is always, you can see here, it's I. They're using I and J in the box at the bottom. It indicates the position in the matrix. You can always find, if you look at a number, if I said it's K32, you know it'd be in the third row, second column, because the first number is the row, the second number is the column. And typically the way you write this is not NN, it's NM. NM. So N is the row, the first digit N is in Nancy, is the row, and the second letter M, like in Michael, Michael, would be the column. So that's the way we typically use our indices. We refer to that as index notation or indices to indicate where in the matrix a particular element is at. Okay, so a little bit more about in matrix notation. Something that's important is what we call the transpose of a matrix. So a transposed matrix is where we take a matrix and we exchange all the rows and the columns. So you can do this for any matrix, right? If we just go back, if you take all the K2 ones here and put them here, so if I take everything right here and put it here, and so everything in this column and put it in this row, and then take everything that was in this row and put it in this column, and then do that for this area too, and then this one, and so on, just keep doing that, that would get the transpose of the matrix. And so you can see that the matrix that has all of its rows and columns switched. So column 1 is now row 1, column 2 would be row 2, and so on. So this is sometimes you do this in matrix manipulations. This is often done. Where it's really important, the reason I'm telling it to you is when you're reading through the textbook, you're going to see this a lot, because whenever we have a column matrix, if you write a column matrix in a textbook, we have text above it, we have text below it, and then you're going to have a ton of white space. So in the textbook, they always write the transpose of a column matrix or a vector, because we just want to save that space. Instead of your text being down here, where you see my laser pointer moving across, your text can now be up here. It saves a ton of white space, which is saving paper, which is really good for the publisher. So in the textbook, you'll see whenever you see a transpose of a matrix, here's the matrix, here's the transposed matrix. You just see a superscript T right there. That just means a transpose. So when you're reading through the textbook, when you see that, it's just don't be alarmed by that. It's still this column matrix. They're just showing it as a row matrix here like this, just to save space. Okay, so we'll see one other place where I'll show you a transposed matrix. We don't do anything with it. I just show it to you. Something that computer software typically does, just so we can see it. One other note here. So we're just showing you some of the basic matrix notation. If you know nothing about matrices and you need to learn a little bit more about matrices, we're not going to do a lot of matrix notation manipulation in here. We'll do a couple of very simple problems where you aren't really doing the matrix manipulation. We'll just show you how we use a matrix, and we will really just go back to solving systems of linear equations. We're never going to invert a matrix or anything in this class, because we just don't have the background in linear algebra. You don't have the background in linear algebra for most of you. But if you do, or if you are hearing terms you have no idea what you're talking about, or you want to learn a little bit more about linear algebra, or you need to learn more of the basic concepts, there's a really good introduction to matrix algebra that you can get from Access Engineering. Access Engineering is free with your ASCE membership. If you go to the ASCE website, search for Access Engineering, you have to log in. You can, within a few clicks after you search for it, you'll be able to find how to get into Access Engineering. And then once you're in Access Engineering, do a search for Shalom's Outline for Linear Algebra, and it's got all kinds of information about matrices once you're in there. And that's how you can get a lot more information. We're not going to discuss it too much in this class, but if you get stuck and you start not understanding anything I'm talking about, go and review some of that, and it'll get you up to speed. Okay, a little bit more notes on matrix algebra. How are we actually solving? How do we actually solve for our maybe our forces or our displacements when we're doing a matrix structural analysis problem? Well, as we talked about in class, the problem that we're actually solving for when we do matrix structural analysis is we have a stiffness matrix multiplied by our unknown displacements is equal to our known force equation. Our force vector. So we have our known force matrix. The way we solve for this is we invert our stiffness matrix, what's called matrix inversion. So we get the inverse of this. It'd be similar to if you were doing typical algebra where you take this and move it to the other side of the equation, where you can't just divide in matrix, you need to invert the matrix. So you get the matrix inversion, then you have delta is equal to k times f, k inverse times f, and that solves for your unknown displacements. And now you solve for your displacements. Once you know your global displacements, you can go back and solve for your unknown internal forces. And it's very simple to say that. Matrix inversion, if you have very small matrices, maybe up to when I was a student, they made us invert like 6 by 6. That was expected to be done very easily. It's easier said than done. But 3 by 3, 4 by 4 are very easy to do. If you have software, you can invert huge matrices very easily. Um, just a little note though, this is where computational time is needed in your software, inverting that matrice. Everything else that you do, the computer can do instantly. It's very easy. Most matrices the computer can invert very easily, but you get very, very large problems. When a computer takes a long time to solve the problem, it's taking a long time because it's taking it a very long time to invert that matrix. These matrices can get huge very quickly in a very simple 2D truss problem. Let's just say you can get a 20 by 20 matrix without even thinking about it. That would just be like 10 members or 10 joints. So if you have a building that's in 3D with beams, even a small building, you're talking about matrices that are in the 100 by 100. So to invert that becomes very computationally expensive. So in the research area of finite elements, particularly in the early ages, a lot of time was spent in not only finite elements but matrix methods and matrix algebra. A lot of time was spent on how to make this more computationally efficient, improving that computational time. A lot of time is spent on tweaking programs. If you write finite element programs, a lot of these programs are written by engineers, not by computer scientists or computer engineers. They're written by structural engineers, really. So a lot of time is spent on tweaking the programs to make them more computationally efficient by making those stiffness matrices a little bit smaller by restricting degrees of freedom so you can make your active stiffness matrix smaller. All this things like active stiffness matrix will make a little bit more sense as we progress in the course. Another thing to note, a singular matrix is something that cannot be inverted. It's kind of like dividing by zero. So a singular matrix, we'll talk about what a singular matrix is. It's something that cannot be inverted. A stiffness matrix by itself, before we do anything to it, before we define our boundary conditions, is a singular matrix and cannot be inverted. We also have one more terminology I wanted to point out. It's what's called a symmetric matrix. So a symmetric matrix, by definition, the transpose of it is equal to itself. Am I saying that right? Let's see. A symmetric matrix is defined as being equal to the transpose of itself. So A is equal to A transpose, which means every column is equal to every row. So any row is equal to its same column. So row 2 is equal to column 2. So if we just look at a particular one, let's just say this one. If we look at this, if we looked at, say, column 2 is 276, row 2 is 276, the same thing. If you looked at any other row or any other column, that would be true. That means that's a symmetric matrix. What it also means, if you looked along the diagonal here, 5, 7, 8. So if you look at 5, 7, 8, we always go from top left to bottom right. it's symmetric about that line, right? -1, -1, 2, 2, 6, 6. So it's symmetric about that line 5, 7, 8. And that's basically what I said. So column. So in other words, what did I say here? Each column and row in the same position, column and row 1 or column and row 2 have the same values. Yeah, so column and row 1 or column and row 2 all have the same values. Okay, so that's a symmetric matrix. So those are some of the terminologies we'll be using throughout the course. Oh yes, one other thing. Obviously, if it's symmetric, if the columns and rows are the same, it must be a square matrix. Otherwise, it can't be symmetric. Okay, so let's talk a little bit about degrees, what we call degrees of freedom. So degrees of freedom. So, what is a degree of freedom? Obviously, it's somewhere the truss can move. So, if we look at a 2D truss member, so if we just take a 2D truss member, let's look at this guy right here. So if it's an axial member, we know it can only have forces along its length, right? We can only have forces along the length of this member, looking at the upper picture, and it can only have deformations along the length of the member, right? So I said displaces along its axis, I really meant deformations along its axis. So there's no shear and there's no bending. So there's only axial forces and axial deformations. Now, if we have this thing where we have forces that are acting, let's just say in the x and y direction, what do we do? And the movement is restricted. Let's say it was a roller, so that it moved up like this. So it moved up like this. So let's just say there was some sort of roller so it moved up like this. Well, what do? We find the components of the forces acting along the length, right? We find the forces of the component of the forces acting along the length, and we find the forces acting along the length, and we find the components of the displacement, so that we can find the displacement along the length. So that's how we find it. So for a 2D truss, we only have degrees of freedom that are acting along the length of the member, but they're only acting in two directions. So only along the axis. So that's continuing that kind of thought process. When we're in a 2D truss, for our 2 degrees of freedom, we only have displacements in two directions, right? We're not talking about rotations because we don't have moments. We're only talking about displacements. So we have two displacements. We have a displacement in the x direction. We typically call that displacement in the x direction u, lowercase u. Positive if we're in positive the x direction. I showed this one as negative, but put the double-headed arrow. And then we usually put a subscript on there. So if we're talking about a displacement at joint B in the x direction, we'd call it u sub b. Displacements in the y direction, so the displacement of joint B in the y direction would be v sub b. So our 2 degrees of freedom for joint B are ub and vb. So that's for a 2D truss. So that's how we call, I think I had one more thing to pop up there. There are x and y directions. Now, if we were in 3D, we would just add one more displacement, and that would be in the z direction, right? In this case, positive would be coming at you straight out of your screen, and that would be w, lowercase w. So for our 3 degrees of freedom at any joint, any one of these joints in 3D would be u, if we have b, u sub b, v sub b, w sub b. So those are what we call our degrees of freedom. There are important things that we're going to discuss in this course, and we're going to be discussing several things. It's our coordinate system is one. We'll talk about that next, and our degrees of freedom. So we always need to know what those degrees of freedom are: UB, VB, WB, and we'll see in a second, theta, rotations. And here we are, rotation. So if we have I don't know why that's animated. If we're talking about a two-dimensional beam or a frame system, we are going to have a 3 degrees of freedom. We're going to have the same displacements, right? We're going to have a displacement in the x direction, which is u, a displacement in the y direction, which is v, still with those subscripts of the joint label. I left those off here just to save space. So if this was joint A, it'd be u sub A and v sub A. And there's going to be a rotation. There's going to be a rotation about the x-axis. So it's kind of shown weird here, but there's going to be some sort of rotation. How much does that joint rotate? So the joint rotation is going to be theta. So there's a joint rotation theta. So if we're in 2 dimensions, we have 3 degrees of freedom at every single joint. There's there's u, v, theta. So if this was joint A, it'd be u sub A, v sub A, and theta sub A. So those are our degrees of freedom. And then if we go into 3 dimensions, we add an extra displacement degree of freedom in the z direction. So using our right hand rule, remember, we put our hand at x, curl our fingers towards y, our thumb points in the positive z direction. That's why z comes out of your screen. And then we add 2 more rotations. This theta is actually a rotation about the z-axis. It rotates around the z-axis. We'd have another rotation around the x-axis, and then we'd have a third rotation around the y-axis. So when we go to 3 dimensions and we include rotations, we actually add 3 degrees of freedom. So if we're talking about a full 3 degree of freedom, a full problem, a full 3D problem, where we allow rotations, we have 6 degrees of freedom when we're in the 3D realm. And we're in the 2D realm, we have 3 degrees of freedom. And again, I said that we're using that right-hand rule. So those are degrees of freedom. Generally speaking, with frames, we have 3 degrees of freedom in the 2D realm and 6 degrees of freedom when we're in 3D. Now, coordinate systems. If you had me for structural analysis, you've probably heard me talk a little bit about coordinate systems when we talked about software. And the reason we talked about coordinate systems just a little bit is because if you remember in a program like StatPro, when you looked at the moment diagrams might not have had the right sign that you thought it would have. You might have thought you'd see positive moment and you had negative moment. You might have even seen in the axial force diagrams, you might have seen what you thought would be tension and it showed you compression. And the reason for that we talked about was because of what we called the local coordinate system. And I might have just kind of shown it on the board real quick and glossed over it just to explain that real quick. Well, here let's talk about that a little bit more in depth. There are 2 general coordinate systems that we talk about anytime we talk about matrix structural analysis or the finite element method. And that's what we call the global and the local. There's a misprint here. It says degrees of freedom. That should say coordinate system. Coordinate systems. So when we're in the global coordinate system is universal to the entire problem. The orientation does not change. It's constant no matter what member we're looking at. I don't care if I'm at member BC, CD, GH, AH. It does not make a difference. And it's what we would typically refer to as our kind of quote-unquote standard X and Y axes. So we have our X and Y axes here. It's unchanging, right? I'm looking at my design when I start drawing it in my piece of paper or in my computer software, whatever it is, the orientation does not change no matter what. If I rotate it in the computer software, the orientation changes with it. That is our global coordinate system, never changing. Our local coordinate system, though, is dependent on the member. That is drawn based on our member. So it changes for each member. Its orientation changes based on the member location and what I would call the numbering. If I draw this as shown here, going from A to B, B to C, C to D, and so on, then as I draw these members, assuming every member was drawn going from the lower alphabet to the higher alphabet number there, not number but letter, then every member would be drawn in that order. And typically local coordinate systems are labeled x, y, y prime, x prime, y prime, not x, y, and then z prime as well in 3D. So if we just kind of look at an example of that, if I start by looking at BC, so if we looked at BC and I labeled it 1 and 2, I'm going to label all these 1 and 2. B is node 1, C is node 2. So I started at B and then I'm going to C. So B to C. So if I'm starting at B and I'm going to C, your x-axis starts at B and it goes towards C. So my x-axis starts at B, goes towards C. Using the right-hand rule, y goes positive upwards from B then. So I have x prime goes from B towards C, y goes upwards from there. There is my local coordinate system for my member BC. Happens to be exactly the same as the global coordinate system. So sometimes your local and your global are the same. So that's for member BC. Well, let's look what happens if we go to member, say, GH. If we go in order from GH, node 1, node 2, so x prime starts at G and goes towards H. Using the right-hand rule, y would go positive downwards, right? So there's my local coordinate axis for member GH. It looks like that. So very different than XY. If I go to member AB, start at A, that's node 1. Now node B is node 2 for member AB. So now if I look at that, x prime goes from A to B, y prime comes out. So my local coordinate system for AB is now oriented like this. So you can see your local coordinate systems are changing depending on what member I'm at. So this is, and we'll see why in a different video, but for each member, it has its own coordinate system that's oriented with the x prime along the axis of the member, going from the beginning to the end, and then the y prime being perpendicular to that. And then the global coordinate system is unchanged. So that's one really important thing to note about coordinate systems. Now another thing, I keep saying node and joint. I've probably even said member, maybe even element. You might not have any idea what I'm talking about. So let's define those. When we talk about nodes and joints, a node and a joint. So technically, if we go with the most technical definition, they're not the same. They're not the same, although we use them interchangeably. And there's a good reason for that. The reason is that every single joint is a node, but not every single node is a joint. So let me say that again. Every joint is a node. So every joint, I'm pointing to B here, B is a joint and it's a node. So every joint is a node, but not every node, you could have a node that's not a joint. In this class, almost all the time you're going to have a node that is a joint. But you can have instances where a node is not a joint. So where that happens is sometimes you can have, we'll talk in a second what an element is, but you can have a single element, a single finite element that has multiple nodes on it. You only connect this element at the ends. So you would only connect it to another one at node 1 and node 3. You have this node in the middle that you would never connect it to. And so what happens is a joint is where you connect two things together. If you take a node and connect it to another node, that node becomes a joint. So if I connect node 1 here at B to something else, then that becomes a joint. Well, since I never connect node 2 to another member, another element, then node 2 is never a joint. It's always just a node. So that's why not all nodes are joints, but all joints are nodes. So that's the difference there. So I use the terms interchangeably because I know the difference. You can use the terms interchangeably because it doesn't matter. But that is the technical difference between them. The other one I keep using interchangeably are members and elements. So this one can also be a little bit tricky. So again, they're not the same. All members are made up of elements. All members are made up of elements, but all elements are not members. So to get the difference here, if we look from C to D, if C to D is one continuous element, right, a single element that spans from C to D, then that single element is a member. If we divide, let's just go from D to E, if we divided that element, we subdivided it into two separate elements. We divided that member. So if we subdivided that member that goes from D to E into two different elements, so I drew one element that went from D to D prime and then from D prime to E, then the member is member DE, The two elements in between are not members. Those are just two elements. I have two truss elements. So that's kind of the difference. I have two elements that make up the member, but the member is member DE. So again, they're used interchangeably, but technically if it's a structural element, so from C to D, so there you go, getting a little bit confusing there. If it's, the member is member CD, if it's made up of a single finite element, then that element is a member. If I use two different elements, then each element is not a member. The whole thing is a member. So again, in this class, I'm not going to get hung up on terminology. You'll hear me say element, you'll hear me say member. I've kind of been doing this long enough that I kind of know the difference, although I may get it wrong occasionally. The important thing is just to kind of generally understand the difference there. I'm not going to, yell at you if you get one of those wrong. Okay, so there is a little bit of an introduction to some of the terminology of matrix algebra, a little bit of the terminology that we'll use throughout the course when it comes to the finite elements and the matrix structural analysis as well. Hopefully that gives you a little bit of an understanding of the terms I'll be throwing out there when it comes to those two components.